Hello, I'm Roy from Masterflow and happy to have with me today Keith from the Pump Industry Association. We're going to present a typical application to you where we were called up after the pumps had been installed and the pumps were noisy. We're going to talk about what the problem was and how this could have been avoided, in the hope that you can learn from this presentation and apply these principles to your next design. This particular project was at Honey Suckle Drive, Newcastle. On the screen here, we've got 3 condenser water pumps and they are feeding off an open cooling tower, which is over this part. We'll come to that photo shortly. So we have a mag flow meter on the suction line coming into a common header and then branching off to each Baker block horizontal motor pump. We then come out of the pumps and discharge off and head to the field. This particular pump is a smaller size than these two because this pump is feeding the tenancy condenser water system, whilst these 2 pumps here, which are larger in size, are feeding the chilled water system. At any given time, we could have one of the pumps feeding the chiller system and the tenancy condenser water pump operating at the same time. What we don't have is all 3 operational at the same time. So it's either one of these 2 larger pumps operating or one of those plus the tenancy condenser water pump. This is the cooling, looking at the cooling towers. So we're coming up on the screen here, we've got the common header and the balance line. This is the balance line, and C is the common header that goes to the suction side of the pumps. So back to the pump plant room. Keith, tell us what you see with this plant room.
Yeah, well, I guess I've got questions about the suction manifold. And you can see that the suction manifold here is a larger diameter than the branches that are going into the pump suctions. So there's potential for trapped air in that part of the suction line unless you can bleed the air out of it. And if you've got air trapped in that manifold, that will affect pump performance and you expect the pump to underperform as a result of that trapped air in the suction line. So that's point number 1. Can you bleed the air out of the system, and is it done reasonably frequently to make sure there's no trapped air in the suction line?
I can see on the pipework, Keith, there is a manual ball valve here on the branch, on each branch. Is that sufficient to get rid of the air?
No. I mean, it's in the wrong place to get rid of the air in this larger pipe. What you need is, at the highest point of that suction line, to have a bleed valve to get the air out.
That's because air takes the easiest path, is it? And going down a branch is not?
No, it's a question of where the trap is. I mean, at the end of the day, the centre line of this small pipe is on the centre line of the bigger pipe, which means that there's a vacant area above that could have air trapped in it.
I'm just noticing too, we have a dead leg here. I know it's often done in the industry, but best practice is this should have been an elbow.
Don't think it makes a lot of difference, to be honest with you.
Okay.
Because you're talking about friction loss. Mm-hmm. Okay. And change of direction. Abrupt changes of direction on pump suctions are generally to be avoided, that's for sure. But you've got them here and here anyway. So, I mean, it's a question of how far do you want to go to avoid disruptions and turbulent flow and all those sorts of things through bends and tees.
So tell me, you talk about evacuating air. From my experience on the tools, I've found that when the pumps are operational, if you were to open a valve on the suction side, you can actually draw air in, especially if the pressure available is very close to the pressure required of the pump.
Well, the only thing that's important whether air comes in or goes out is what is the pressure differential across that ball valve. If the pressure in this suction pipe is higher than atmosphere, air will come out, and if it's lower, air will go in. It's that simple.
So back to the noise that was first reported about this installation. There's a couple of things we're going to look at here. Firstly, we're going to look at pipe sizing and the plumbing, general plumbing here, and then we're going to talk about the pump sizing. So let's have a talk about the pipe sizing. The branch from each pump was 80mm, going into a 125mm header. The pump suction was 80mm at each pump. So what do you see here, Keith?
What's the size of this pipe?
This was 100 millimetre.
So going into 80?
Yes.
So, okay, you need an eccentric reducer at these connections. Otherwise, you're going to get trapped here.
I see what you mean. You mean that's not an eccentric reducer?
No, that's not an eccentric reducer. That is a concentric reducer. An eccentric reducer has a flat top and a sloping edge to match the pipe diameters.
So where do you can't use concentric reducers on the suction?
The general principle for pump suctions is you don't want trapped air in this line. And if you've got a concentric reducer, you've got a potential for trapped air all along there.
Sure.
And trapped air means pump underperformance and potential for noise.
Now we're going to look at the pump performance curve and see what actual pump was selected. You can see from the performance curve that these pumps have a nominal speed of 2,900 RPM and the flow rate is as detailed on the curve. So we can see when you do the calculations on the flow rate that we're running quite high velocities through 100 mil and 125 mil pipework. What's your thought around pipework velocities, Keith?
Well, generally speaking, I'm looking for relatively low velocities in the suction pipework. Potentially they can be should be lower than they are on the discharge side of the pump. If you talk to various people, they will suggest that 1 metre a second is a reasonable flow rate for suction pipework.
So our pipework velocity in this situation was 2.9 metres per second. What are your thoughts around that?
Which piece of pipe are we talking? Because they're different diameters.
Certainly. Certainly. So we had 2.9 metres per second in this 125 millimetre header, meaning that it was higher going down the branches.
It's got to be higher going down the branches. So normally speaking, we're looking for velocities into the eye of the impeller of around 1 metre a second. Okay, that's good for a suction design.
So let me ask you then, why do they make a pump with an 80 mil suction and at 2,900 RPM, the velocity's much, much higher?
Because the pumps are built to a standard, and that standard is either an ISO or a DIN standard for an end suction pump, and then there are nominated flow rates and there are nominated flange sizes. But what we're normally expecting to happen is that the flow or the pipe alteration in diameter takes place very close to the pump suction flange, and that it's an eccentric reducer. So you've got a relatively smooth path coming into the eccentric reducer and going into the eye of the impeller. Because you've got to remember that in this particular pump design, we've got liquid coming in this direction and an impeller rotating in that direction, and you want as straight a flow as you possibly can going into the eye of the impeller for good hydraulic results.
So in conclusion, it's very important that you're sizing your pipe work for the right velocity and that you're selecting a pump that has as lower net positive suction head required as possible. In this situation, the net positive suction head required was 4.89 metres. It's very important to always check the NPSH when you're dealing with condensed water pumps on an open cooling tower. I'm talking primary condensed water pumps, not so much secondary condensed water pumps, because secondary condensed water pumps are generally on a closed loop. Open or primary condensed water pumps on an open loop. So with a 2,900 RPM pump, the speed is given up here, 2,900 RPM, our net positive suction head required will be much higher than on a 1,450 RPM pump. Had a 4-pole pump been requested and supplied, we would have not had this issue here because this figure would have been much less.
Yeah, well, that's a function of pump speed, isn't it? NPSH performance is related to the speed of rotation of the impeller.
So the smaller the less the speed, the smaller the pressure required.
Generally speaking, yeah. Obviously, you wouldn't have the same pump anyway if you're running at 1450 because it would be a larger pump and you'd have larger suction connections. So everything in that regard is contributing to a more favourable situation. If you've got suction problems very often a 2,900 RPM pump is not a good solution.
Our recommendation to you as the contractor or the consultant is don't try to save money with a smaller pump, i.e. a 2-pole pump, and minimising your pipe work diameters. Design it properly, and this will save you a lot of hassle down the track.